Okay, good morning, everyone. Our next keynote lecture is from Professor De Cheng Wan. The title of his presentation is Numerical Simulation Techniques for Water-Air Bubble Mixture Flows. So let me briefly introduce Professor De Cheng Wan. Professor De Cheng Wan is a Yangtze River Scholar Distinguished Professor and the Director of the Center for Marine Hydrodynamics at Shanghai Jiaotong University. He is an Elsevier Global highly cited scholar and has won the International Ocean Engineering C.K. Kim Scholar Award and serves as the editor board members of 8 international journals. So, Professor Fan, you can start your presentation. Thank you.
Thanks, Professor Yao, for your kind introduction. First of all, congratulations for Professor Chen Zi and Peking University successfully organized this open forum workshop. I remember this is the second time open forum workshop held in China. Yeah. Also, I thanks the organizer committee invited me to give this keynote presentation. Let's have a chance to introduce our recent work about the water-air bubble mixed flow by using the open foam. This problem is very typical in ship flow. You know, when the ship moving in the sea, we always can see it. Very complex, the air bubble water mixed flow. So, but also it's very difficult. So, over the past about 10 years, we work on this numerical to develop the numerical techniques to solve this problem in the open form. I'm going to talk about the 4 parts. First, just give the introduction and what's the water-air bubble mixture flows, and introduce the mechanism behind, and I focus on how to solve this problem. And sorry. So, what's the air bubble water mixture flow? So you can see when the ship moving in the sea, always a lot of foam flow. You see the white flow. You can see along the ship, so you can see a lot of splashing, and so this is a kind of the air bubble mixture, multi-phase flow. So what's the behind of this? You can see the wave breaking, right? You can see the jet blushing, right? Also, you can see a lot of smaller droplet optimization, and also you can see the gas and the water, the treatment. Also, you can see a lot of bubble. You can see this is a lot of the bubble. So you can see this is a very complex interface, right, between the water and the air. But you can see that the jet flow and the droplet and the gas and the bubble. So, and you can see in a different region, they have a different list of phenomena. So, see, you can see this is all with the the breaking, propagation, and the dissipation. And also along this ship only, you can see there's the propaganda and it's the boundary layer interaction with the wave flow. So it's you can see it's a very different phenomena. You see in a different region they have a different phenomena, the circulation. So and also you can see in the stem region, in the stem of the ship, there's a lot of the flow separation and the bubble mixing. So you can see there's a very complex the two phase, the turbulence, this the evolution. And yeah, and also if you see the high speed ship, if the ship moving very fast, so you can see oh sorry. So this air and the water, the bubble, the mixed more obviously. So it's the facilities. So this means related to the ship speed. And yeah, also you can see if there's the sea condition became very heavier, you can see this the bubble, the mixed flow also became very more obvious. So this means it's also related to the sea condition. And also you can see that even if the ship became very bigger, so you can see that along the ship, also you can see that a lot of the white flow, right? So this we can also is the mixed, the air, water, air bubble, the mixed flow. So the speed is not very high, but if the ship became very bigger, so this means also related to the mass of the moving body. So you can see for the container ship, you can see that also is something like this speed is very low, right? But you can still see a lot of the white flow, right? So so this means also this is the kind of phenomena related to the mass of the ship flow. Yeah, you can see why this problem is so important. Here I show you one example. So this is a hydrofoil tolling, right, in the tank. You can see if the speed is a little bit slow, like the fluid number is the 0.5. This is the fluid number equal to 1. So in these cases, you can see this the water air mixed flow, not so obviously. But in this high speed case, you can see a lot of the mixed flow, the air bubble, water jet, mixed flow, you can see this is more seriously. Then you can see this is resistance, also we can say the energy is bigger than this one. So if we calculate the energy, the water, the fluid surface, the bubble, everything together. So you can split it to three components. One is the potential energy, kinetic energy, surface energy. All this together, you can see that this is bigger than this one. So this means this the mixture flow. They contain a lot of the energies. And this is another example for the propeller. You know, if the propeller operating in a uniform, this means in a pure water, there's no any bubble. This is the propeller the operating in which the air bubble. You see the background the flow is a lot of the air bubble. So you can see what's the difference. So the perform of the propeller is decreased, even including the torque, thrust. You can see that decreased a lot. So this means the propeller working in a different background flow. So they have a different performance. So this also another example is for the hydrophilic efficiency. We get a very similar result. You can see that. But this is a pure water cases. This is a bubble flow. So you can see this is the flow along the hydrophilic. So you can see the different the performance of the hydrophilics. So you can see that the difference between the lift force under the bubble flow and under the pure water environment can be up to the 20% difference. So you can see this is very important. Another thing is the impact force. So you can see the bubble flow working on this structure. You see, if they have this mixture flow, you can see that there's this process contains 3 stages. First is the instant directed the forces here, and then the second the load of the droplet. So it's you see they have this different, and then the third case is the air cushion effect. So this is pretty important. There's the complexity of the air bubbles. So you can see that if you don't take into account this mixture flow, so the impact force is something like this. But if you take into account this the bubble flow, you can see that this impact force will increase a lot compared to here. So this is very important. If we should take into this the effect of the mixture flow. So what's the mechanism behind? So we just take into account this mixture bubble flow. You can see. So first you can see the phenomena is the droplet, right? Water mist, you see, and then you can see the lot of the air enrichment to the water, right? And under the water, you also can see a lot of the bubble. So you can see we have this the interaction, the complex the interaction, the processing, like the violent impact, the multi-scale mixing, the bubble breaking, the collision, the interface, the formation, mixed set of the interface. So it's very complex. But anyway, here I show you one example. So why is this the first character is the bubble should be persistence, should be the always keeping in the water, you know. So you see, even the breaking, and there's a lot of bubble inching the water, and then its bubble is always keeping in the water flow. So we can see that in other cases, usually the breaking wave, the bubble will be disappeared. See this kind, you can see that this wave breaking, but there's not bubble keeping in the water flow, right? They will disappear. This is not we so-called a mixture flow. And this one, you can see the bubble always exists in the water flow. So then it will generate this mixture flow. So here I show you one example again. So if the bubble rising into the free surface, then it disappear. Then you can see that there's no mixture flow, right? But if the bubble increasing and then not disappear, they always keep in the free surface, then you can see a lot of the bubble flow, right? There's the mixture of water. So you can see there's different cases. So and also you can see this is no bubble. There's many bubble generated, but disappear quickly. So you can see this is no foam, no mixture flow, right? Okay, so this is another cases. The bubble generated and they always exist in the water. So this is we so-called this the foam flow or mixture, air bubble water mixture flows. So this is some difference, right? So what's the, you can see, why this bubble will exist in the water? What's the reason? So the simple case is sometimes if the bubble there's no energy supplied, then they will disappear. So you can see the bubble come here and then disappear because they cannot get the continued energy support. But if the bubble can get the energy, continue the supply of energy, then the bubble will keeping on the surface, in the water. So the bubble will exist always in the water. So you can see something like this. This means the bubble flow is continued during the water moved and slowly diminish after the body stops. So if it's moving, you always provide the energy into the water. The bubble will be exist continually. So another one is the droplet also is the consistent. They not disappear. You see a lot of droplet generate. Then also they can also still continued. So you can see the first the moving the body, and then a lot of the jet flow diffusion, the interface friction, and then you can see a lot of the droplet generate. So you can see there's the first breaking to generate the droplet, and also second impact to generate the droplet, and then the droplet you can see always the persistent in the air. So also you should provide the continued energy into the little droplet. And also the third one is the transition between you mean the air, the bubble, the droplet, and the fog, they can be change each another. So you can see sometimes this is a droplet, sometimes they inch the air into the water, then become the bubble. So they transitioned always continued. So this is you can see always the state was the transport. So and also you can see the time scale and the space scale also is the larger the fairly change very largely. You see, we can see that this the flow. The foam flow, the mixture flow in the long scale, you see, even the kilometers. Also, you can see in the local, is the meter. Also, you can see the very micro local. So you can see what's the smaller droplet, the smaller bubble. So you can see the spatial scale, the covered very larger length. And also is the temperature scale. Also, you can see that they can last a long time, right? Even several hours, 30 minutes. And also, you can see when the splashing flow, you can see the last very short time, 1 minute or 10 seconds. But also, you can see that this the bubble flow. It's a milliscale seconds. So it's the time scale and the space scale. So how solve this the problem? So we try to solve this the problem. At the moment, you can see have many method to solve this problem. One is the interface model. So and another one is the non-interface model to solve this problem. In the interface model always can be specified the two ways. One is the VOF, another one is the level set method. If we use the non-interface model, we have an Euler-Lagrange method and Euler the method. So at the moment we have this kind of numerical method to solve this one. So first is the VOF. This is pretty useful method. So I don't pretty detailed give the list. So you can define the list phase function. You know, H. Once the fluid phase, the air phase, then you can get the volume friction. So the C, something defined here. So you can get the C function, and then we can governing the equation for the H and the C. So this is for the list. But how to solve this VOF equation? There's two ways. One is the geometrical VOF, another one is the algebraic VOF. So for the geometrical VOF, you know, you need to reconstruction the interface, right? The advantage is the very high precise of Elizabeth captures. But the disadvantage is the calculated of Elizabeth reconstruction is more complex and it's very time consuming. Another one is the algebraic VOF. So the F function can be increased function, you know, like the polynomial hyperbolic tangent function. Without you can see that there's no needed flexible reconstruction. So the advantage is the calculation process is much simple, easily to program. But the disadvantage is the accuracy is a little bit low. So here I show you one example is the sync method. This is the algebraic. It's the algebraic VOF method. So you construction this function for the interface, right? It's the hyperbolic tangent function to solve this. But you see there's a smearing of the interface here a little bit. So here is the example we use the tangent the method. You can see that we can capture the bubble rising. So they can solve the two-phase problem, right? Then also can get a good result. You see when the bubble rising. So and the problem in the VOF and sometimes the mass and the momentum they cannot keep the consistent in the whole calculation. So here we change a little bit. We keep the rho and the u together as the 120. So we keep the mass equation and also the momentum equation. We use the rho and the u as the similar variables. So then we can keep the mass, the momentum, the consistent advection. So then this keep this more stable and also decrease the dissipations. So if you like this, so for the equation, for in the two-phase equation, we always keep these two together. So we always keep these two twin. You can see this together. So we shall change this formula a little bit. Another thing, we try use the adaptive, the hybrid scheme, because as I said, always this time scale and space scale they have a larger change. So we use the adaptive hybrid scheme. So we use this beta and to change, select in a different region. You see, in a different region, we use the different the scheme. So this is it's not so changed quickly. Then we use the low accurate scheme. If the change quickly, we use the more quickly. Another adaptive is the use the grid system, adaptive grid techniques. You know, for this the small variable, we use this kind of adaptive grid techniques. One is the expansion operator, you know, from the for the use the Lagrangian interpolation. Another one is the restrict operator, you know, is from the coarse scale to the fine scale. So this is for the small variable. If this change quickly, this is the discontinued variables. We use this coarse to find prolongation operator, and this restrict operator to find the coarse grid. So this we can avoid this unstable the phenomena happened. So I show you this one example. You saw this is the bubble coalescence. You know, you see these two bubble and the imaged together, and then also this the unstable. You know, the free surface unstable. So if you use the technique adaptive techniques that you can capture the very detailed this the unstable of the ship hulls. So here, this is another example is the jet flow. You see, this is one jet into the side. Then you can see a lot of the bubble and the jet flow the internet. So when the jet velocity is 25, this is 30. This is more serious. You can see that we can get more white this the jet flow. So if you don't use this adaptive, then it's very hard to capture this small jet flow and also this bubble. Okay, so this is another example for the breaking, for the wave breaking. So here we use you see this is the grid adaptive technique here. You see we change the scheme and the grid system when the wave breaking happened. So you can see what's the breaking and the jet flow and the bubble flow generated during the wave breakings. So here I show you the whole process. How was the wave breaking and how was the air inched into the water, and then the bubble generated, and then the bubble keeping existing in the water flow. You can see the how was the you can see the how was the bubble generated and breaking and this the structure of the turbulent flow that happened, the interaction with the free surface. So you can see the bubble always keeping in the waters. So you can see that always this bubble can be keeping in the waters. Yeah. Okay, this is we use another color. We use the color to distinguish the vortex and the bubble, and you can see the clearly what's the bubble, what's the droplet. So this is another example is the jet flow. You see this is one jet flow. You can see how was the air inched into the water, and then you can see a lot of the bubble and the jet flow mixed together. So you can see the very detailed this structure of the jet flow and the bubble flow mixed together. So another one is the level set. We can see the level set. Level set is we use the standard distance the function to represent the interface, right? We introduced this kind of the distance function phi to represent the interface. So and then we solved this governing equation for the distance function, but we always should keep this function phi as the distant function. So you should always keep this one. But you know, this is very difficult to keep the phi always the distance function. So you should always do the initialization. So this is two process for the VOF and the level set. You can see what's the difference, right? But always they solve this is solve the friction function. This solve the distance function. Yeah. So here I show you one example, the bubble rising. So this is we use this level set. But if didn't do the reinitialization, the mass will be lost. This is not a key, not a conservative. But here, this one, you do the initialization, then you can keep the mass concept. Then you can see a lot of the smaller this bubble. More clearly. So this is more accurate compared to these cases. So for the level set, we always should keep this mass distance, and also should do the reinitialization. So we can see that we have the advantage over VOF. Also as a disadvantage. Also level set, you can see it's easy to get the interface between the water and the air. But also there's a disadvantage because the mass conservation always not keep it very well. So the next step, so we want to couple this together. Level set and the VOF, couple these two methods together, so get the CLS VOF. So you can see that what's the, sorry, I don't know, why is the no function? Or maybe, I don't know, this is the pom-pom the problem. Yeah, so this is a VOF, the function, and then we can couple this together, we use the reconstruction interface, use this PLIC method to construct this then activate the volume friction up, and then this distance function, then the reconstruction intersection this again, in this distance the level set phi, so we initialize the phi, so we can couple in this VOF and the level set together like this, so. And then we can discover this one cell into the multiplied tangent this cell center and the phase center, and so this is very easy to do, to implement. And also you get the interface in the PLIC. So you can do like this, right? Then we can get the gradient of the phi, and then we can get the constant d. So always use this function. You see on this the cell. Then we can do the initialization. Yeah, or I don't know why is there no formula. Okay, this maybe a pom-pom that can copy the problem. Okay, anyway, there's no formula. Okay, sorry. It's terrible. Okay. Yeah. Okay, I just show you example. So then you can see we can use if we use the VOF here. This is a level set. We can keep the good result, right? No problem. But we can compare detailedly. You see, VOF of phi, So you can see the dissipation of the final stage. You can see that not so clearly, right? A little bit weaker in this region. But if you use the coupling the label set in the VOF, we can get very clearly this final stage in the breaking of water something. So you can see that this is a little bit better than compared to the VOF or level set. So this is the coupling the level set and the VOF is much better. So I show you another example, the 3D condition. As you can see that, one the bubble and then the deformed, and then they can come back again. You see, we can compare over the calculation compared to the another simulation. So you can see that we can give the result. Especially you can see we give the section in the different. You can see that we can get a very clearly this the distance, right? So you can keep it very good. Even this section, if any kind of section, you can always keep the good distance linking. So we show you example. This is the bubble flow, the jerk flow. So this is one plate. This is the coming flow along the bubble, right? This is a benchmark case. So you can see. I show you this one example. So how was the jet flow generate and entrant into the water, and how to was the bubble floated in the water. So you can see this. You can capture the every bubble and every jet flow along this plate. So now I can show. Show you. You see that in a different time the instance, you can see the how was the jet flow generate, and you can see the splicing, and then the injected air into the water. So it's breaking, and with the bubble, with the jet flow. So you can see that in the every stage. So then this is compared to the experiment. This is experiment cases. This is of the simulation. So you can see we can capture the splashing of this water is more clearly. You can see this very clearly. These regions, and this is an experiment. This is of the simulation. Also, we can get the ball with the hair and the ball with the crystal. So we get the statistic, the volume of the ball with crystal and the ball with hair. So you can see this compared very well. So this is static. So this means the simulation is compared very well. Experiment result. So also we can see this is the profile. You can see that this is over the numerical result. This is an experiment. This is a series predict. So you can see, we can get a very good result compared to the numerical result. So, and also we can see the flow structure, especially the turbulent the structure in this the mixture flow. So you can see is the rotating the air cavity. You can see something the air water the structure, the turbulence the structures. You can see very clearly the rotation the air cavities. And okay, then we can get this gas, volume friction, the temperature evolution. You can see in this stage we can see a lot of the air into the water. So this means they have bigger gas volume friction. So you can see that in this stage, this means there's a lot of air inched into the water. So this is more clearly to see that this phenomena. So also you can see how was the previous the distortion, the propagating during this with breaking the bubble flow. So also you can see some distortion of the surface, and also you can see the air cavity, the formation, the generate. So you can see the white and the water appearance. That you can see the more clearly, right? And also you can see the weak flow. So there's the first weak flow, the second weak flow, and the third visible weak flow. So it's a more complex the phenomena we can see that. And also you can see a lot of the increment of the air, so into the water. So this is we can take it. And also you can see that this is the bubble. Containment that is the volume. You see, sometimes in if you use the bigger angle of the plate, so you can see that increase the angle of the inclined plate. So there's the bubble is the different compared to here. So they can get more the bubble this one. And also you can see to analyze the bubble size, distribution, the spectrum, you know. So what's the, you can see the which the time the increased, you can see the how was the bubble size, the distribution. So you can see in different time step, the bubble distribution, the spectrum also is different. So you can see the bubbles increment, the voltage structure. You can see the so actually this is the interface, the turbulence, the structures, the bubble flows. So you can see what's this structure. So I mean you not only see the bubble flow, the index mixture flow. Also you can see a lot of the turbulence, the voltage structure inside. So this is a pretty complex structure flow. Okay, I show you another example is the surface piercing the foil. So this is a hydrofoil, you know, foil around, you know, it's not only plate, but it's a hydrofoil. It's something like this. This is image that the depths. So this is the geometry parameters. So I show you example. You can see how was the water flow along, and then the bubble generate, and the jet flow. You can see that. Yeah. So you can see what's this bubble generate float. So yeah, you can see that. Yeah. Okay, I can show you. This is a stage is we've run up, right, along this hydrofoil. Then it's the impinge into the flow, and then you can see the breaking, which jet splash in the ball with breaker. You can see and the region, the shape, the hydro jumps. So you can see every stages. So this is a experiment compare with the experiment. This is of the simulation, so you can see the very similar. We can capture this violent form flow, than which many droplets. You see, you can see you can get a very similar the phenomena. So we can also can get all this profile for use the different method which compare the experiment result. So this also you can see compare the experiment result. So we can get a very similar this wave patterns, and also this is streamline, right? You can see get this very complex gymli. You can see especially near this breaking the regions. Okay, so we can see that this very typical 3 stages. This is the initial stages, you know. This is just the second stage is fast developing, you see. And then finally they get a stable stage, you know, always the breaking. This is heterogeneity, and then fast developing to the stage cases. So you can see, I just show you some of the typical instance, the phenomena. So the bubble cloth has a larger penetrate depths into this region. You can see that always, and then the bubble unified. You can see that you can get a similar span-wise directions. So, and also you can see how was the air injected into the water and then get the bubble patch. So span-wise, then we can get always this phenomena. So, and then we can see this very complex turbulent voltage structures along this breaking the hydrofoil and near these breaking regions. So, and can see the oscillation, this velocity along this the breaking regions. Yeah, and another example is the flow along this cubic. So how was the stained regions? So we can get this simulation. So I show you example. This is a cubic, right? This flow along this, you can see the how was the bubble generate, and then propagating in the stain region. So you can see the how was the breaking along this in the stain region. You see, especially here, you can see the how is the you can see it's this region. So and then this one, you can see that this one is this here. So you can see the wave breaking and propagating in the stain regions. So this is an experiment. You can see this is of the simulation. See the compare. We can get capture this very similar and this time average height function along the central line, along this central line. So we can get a very similar this static. So this is the typical cases. You can see the how was the weak flow, the propagating in the stain region. So this is the instance, the bubble grip, the distribution, some statistic complex. You see the bubble and the corresponding distribution. Yeah, you can see the how was this, and also we get the pattern of the bubble cluster. We give some constant the statistical completion. So you can see this is a bubble size spectrum. We can get these spectrums. And also we can see that in this the subsequent view, this is the bubble. So you can see the bubble size distribution always like this pole load relationship. You see the bubble size there, you know, something. So you can get the containing constant of the bubble size, the distribution, and you can see that if you use the different size of this cubic, so you can get a different this standard breaking wave the flow. You can see so different velocity, the incoming velocity different this cubic, so you can get a different form of the ethane. This is a streamline. You can see the whole this the breaking region and the standard region. So as I said, you can see that we can get a different this standard region if you have a different this cubic. Okay, so this is just as I said, you can get the different bubble statistic the compression. And here we have another example for the ship. What we can say is about the ship flow. So here I show you one example is for the ship flow. You know, in the ship the propagating in the water. So with the different trim angle. So you see the we ship can be a little bit. If the no trim, something like this. If we have a trim. So here we have a no trim pitching. This means the very stable propagating. So you can see the hole was the breaking that happened. So you can see this is compared with the experimental result. So we can see we can get capture this the breaking and the bubble and the water jet mixed flow. So if we increased a little pitch. So we get so this is the pitch degree 0.5 degree. So you can see what's the difference, right? It's more serious. So if we use the 1 degree, so you can see not only breaking, you can see that there's a 2 second 2 second breaking wave, right? You can see. So we can capture this 2 second. So I can show you compared. So this is 0 degree. This is 0.5 degree. This is 1 degree. So this is so if the trim angle is more bigger, then you can get a more breaking series, the more breaking the wave. So this is very important. The trim angle effect that is on the ball wave breakings. Okay, so if you can see if we use the different pitch, so this is a little bit different. So the pressure coefficient also is different. So this is very important for the friction. For the pressure also can get as a little different for the volume. And also can see that for the wave height and the local vortex, this is a pitch. You can see they have a second breaking, right? One breaking and the second breaking. How was the vortex evolution along this breaking wave? So you can see this wave profiles. Also, you can see a little bit different. If the trim is about 1 degree, you see the wave aviation a little bigger compared to the 0. So this is more important for the pitch trim, the angle effect. And also you can see the structures. Right, yeah, as I said, you can see the second breaking here, right? But here, always there's no second breaking, right? So this is a much violent compared to these cases. So this is another example. Is coming in a wave. So the ship moving in a wave. So you can see how is the breaking. Happened the interaction with the ship motion. So this is in the future we will do detailed analysis for these cases, because this is a wave coming, and then also the ship also is moving. So this is the interaction between the wave and the ship, and also this the bubble the jet flow is more complex. So here I didn't give the very detailed analysis, just show you the simulation. So in the future we can do more about this wet flow. So this is I talked about the interface model. So as you said, this is very time consuming. So if possible, we use very less time to capture this phenomena. It's possible, but we use this non-interface model. So use the Euler-Lagrange model, and another one is the Euler model. This is very saving the time. But it's not so accurate. We just for the Euler-Lagrange, we use the particle. Use the Lagrange bubble is the particle for the bubble flow. Another one is use the liquid phase. We use the Euler equation. So this is Euler mesh. This is the bubble for the particles. So we can do the I don't know. There's no formula. This is the pom-pom to the problem. Yeah. Let's once for the particle the equation. Particle equation, drag force, lift force, and then also you should take into account that how was the bubble interaction with the wall. So you should take into account that the elastic force, the viscous force in this Lagrange equation for the bubble flow. So, and also we should think about how to solve this bubble fragment and the bubble coalescement. We use this condition to distinguish the wait time. And this is Euler Lagrange method. So this is for the Euler equation, containing some of the alpha. So this is a friction of the bubble. So this is for the flow, phase flow. So this is a bubble flow, the Euler Lagrange solver, something like this. So here I show you one example. This is a bubble into along this plate and the boundary layer flow. So you can see this is a bubble. This is the coming current. So you can see the whole is the bubble flow along this plate. And then you can see the whole is the bubble along this the tender flow. So you can see the whole is the mixture, the bubble and the water mixture together. You can get good result. So you can see the Euler Lagrange. You can see the whole is this is the bubble flow in this is the boundary layer, and this is you can see the general the effect of the bubble flow influence on the water flow. So and then we in a ship we use the air conclusion to reduce the friction, the resistance. As you can see, this is the inject bubble into the water. Then you can see how was the bubble flow along the ship hull. So you can see how was this, and then we can see how this friction, the resistance can be reduced. So this is one example in the ship flow. It's pretty useful to save energy. So another example is the inject. So this here, this is water. Then I inject some of the bubble inside into the water. So you can see how was the bubble flow flowing into the water. So you can see how was the processing of this bubble in the water. So you can get these stages. So another example, another way is the Euler is more simple compared to Euler-Lagrange method. So this is two equation. One is the gas equation, one is the liquid equation, always the in the Euler formula. So we can get this two momentum. This is a mass. This is a momentum equation. Then we can solve these two equations together. But it is an interface between the gas and the liquid. Use this equation. And then we can solve this equation together. This is we so-called equation. So this is one example. This is air and water. This is the air injected. So how is the mixed the air and the water mixed together? So and we can see the one example is the airflow along the airfoil. So we can see the how was the. So if there no air, just the water along you can see the how was the voltage structure along the hydrofoil. If the inject some of the air bubble into the water, so you can see the how was the effect of the airflow into the flow structure and the separation of the water. So you can see the different, right? So if you include air in the coming flow, so you can see there's more separation. It's more easily separation of the water flow. So along the hydrofoil, see, compared to here, see, this is the most stable, but it is became unstable. So this the air cases is very important to influence this. So you can see this the separation. You can see that these cases there. Yeah. So this means it's pretty important for the to take into account the air force. So also you can get the CD, CL, this drag force and the lift force. So it's more unstable if you have more air, coming air in the float, so more unstable. So this is pretty important to think about these cases. So another example is the propeller. As I said, if the propeller working in the pure water, and then compared to the propeller operation in the air water two-phase flow, what's the difference? This is the grid system to calculation propeller. So you can see this is a propeller running in air water. So this is no air. The coming flow, there's no water. This is 10%. You can see that the vortex is the enemy compared to here. You see that it disappeared pretty quickly in these cases. So you can see the KT, the torque force, and the thrust and the torque. So you can see the decrease the a little bit. So you can see the torque and the thrust decreased about 8% and 4%. So this is very important if you take into account the performance of the propeller, which the coming air environment cases. Is no battery. Okay, it cannot work. No battery. Yeah. Okay. Summary. Yeah, I go to yeah. As I said, we can use the VOF interface method. Never said the coupling level method. Yeah. Next. Yeah, and also no interface, Euler-Lagrange, Euler method, but a more low accurate. Yeah, next page. Yeah, still a lot of work we need to do. You know, actually we still not. As I said, we've structured all many conditions more complex the cases, and then the more the evolution the patterns. So still we need to know what the general condition evolution the pattern and the influence the factor behind this mixture float. So next page, yeah. So and how to get the resistant prediction because due to this water-air bubble mixture flow. So we need to know how much the resistance caused by this mixture flow. So usually we didn't take into account this the resistance, but in the full scale we have to think about this part, more important part, resistance. So next plate. Yeah, and also sea keeping. You see when the ship, the lowering the motion in this mixture flow, you can see the foam flow, right? So how was the stable of the ship motion in this very complex environment? You see, they must different with in the pure water cases. Okay, next page. And also, as I said, the propulsion perform. I think you see in the ship region. So at just a moment, I show you in the open water, right? Now in the future, we will think about behind the ship region, the so-called standard regions, how to predict this propeller performance in this the mixture flow environment. The next page. Yeah, and also the important, as I said, it's more the flow became unstable, right? So it's the more oscillation. So the noise, so it became very important in the future. So we should predict how to predict the noise come from the unstable flows. Yeah, next page. So this thing's so important, right? So how to control, how to separate this the phenomena. I think this is also pretty important in the future. Okay, next page. Yeah, okay, thanks my research member, the research team member. So many of work has come from the hard work. So thank you for the hard work. Yeah, thank you very much.
Okay, Ivan, let's hold off a little bit for the coffee break, and we can have time for one small question.
Thank you. Thank you, Professor Wang. I have just a small question. For your post-processing, it looks quite beautiful. I want to know which software do you plot your all the numerical results?
You mean the moving, right?
All other post-processing like that bubble.
Yeah, you mean it's post-processing, right? It's the emulation, right? This is use the tech plot.
Tech plot is okay.
Yeah.
Okay, Professor Wang, thank you for your outstanding presentation and your laborious preparation for this presentation. We have prepared a gift and a certificate for you. Thank you.